So now let's take a couple of examples from cells that are representative of what's in our body. So we have ECF, which is extracellular fluid, that's the fluid around a cell, and ICF, which is the intracellular fluid. So if we take first one particular ion, and we'll do these one at a time. Sodium has a concentration outside the cell of around 145 millimole. Inside the cell is very low, about 12. So there's a gradient across the membrane set up here. If we look at potassium, it is high within the cell, about 120 millimole versus 4 on the outside. Calcium is what looks like to be low on both sides, but in actuality, the extracellular fluid has more calcium in it than the intracellular fluid. Intracellular fluid has almost none, free calcium. And finally, we have chloride, which is high on the outside of the cell and low on the inside. The one other thing you should notice about these various molecules is their charge. Sodium and potassium have a positive charge, and they have a +1. They're considered monovalent. Calcium is a +2. It's divalent. And then chloride is an anion, or a negatively charged molecule. The other thing to keep in mind is which direction the arrows are pointing. You notice that they always point from the base of the highest number to the area of the lowest number. Why? Because all of these molecules want to get into equilibrium, meaning that they would be the same on both sides of the membrane. That is their goal. They want to live in harmony and be the same on both sides of the membrane. The membrane, though, is going to be somewhat selective about which ones it allows to pass. So we can calculate the exact voltage difference based upon those concentrations. Now, it's not important to be able to calculate this on a minute-by-minute basis. They're only going to be numbers in which you have to be familiar with. So, for example, you see that this potential for sodium is around +61 millivolts. So that's based upon the concentration in the extracellular fluid versus the intracellular fluid. And you're going to ask, how in the world did you figure out that that was 61 millivolts? We could have done it in two ways. One of them, we could have put a reference electrode on one side of the membrane and an active electrode on the other side. Or we can use a formula to calculate it, which is called the Nernst equation. With the Nernst equation, you take 61.5 divided by the valence times the log of the concentration inside the cell over the concentration outside the cell. So either directly measuring it or using the Nernst equation, you can calculate the particular voltage that the concentration of those two ions inside and outside the membrane would cause. If we look at potassium, you notice that it also has a voltage. But the potassium potential comes out to be -90. Why? Because potassium was high inside the cell and low outside. Calcium's membrane potential, very high, 120 in this particular example. And again, that's based upon the ion concentration in either the measured value or the Nernst value. Remember, for the Nernst value, this one is going to be different because it's divalent. So you're going to have to take 61.5 divided by now 2, because it has a +2 charge, times the log of the concentration on the inside over the concentration in the outside of the cell. The final ion that we have here is chloride, and chloride is a -52 millivolts. And remember that it has a higher concentration on the extracellular fluid than the intracellular fluid. So the arrows become very important, and their particular Nernst equation value becomes important. So we have +61, +120, -90, and minus about 52. all from the ions that we had, or we directly measured them from this cell. So that looks like there's what, 1, 2, 3, 4 numbers here. What is the cell really at? Do we simply just add up all 4 of those and divide by 4 so we get a mean? That would be too easy, wouldn't it? No. What we need to do is add another factor in play. That other factor is which channels are open and which channels are closed. Because, again, if you don't let the ions travel across, they don't count. So we have to make sure which ions move becomes more important. So let's look at calcium. At rest, calcium is closed. Therefore, we don't actualize that potential of 1 in 120. Sodium channels also closed at rest. Therefore, that plus 61, non-factor. What is a factor? Potassium. Potassium channels are open at rest. Therefore, an excitable cell will have a negative membrane potential. Because there is a conductance for potassium, it will be more likely close to the potassium equilibrium, which is minus 90. So there will be some cells in the body that are at a minus 90 if these cells are open all the time. Most cells, though, are not at minus 90. They're a little bit above that, and that's because of one other factor, and that's the sodium-potassium pump, or the sodium-potassium ATPase, which is constantly cycling and cycling and cycling, moving what? Potassium back into the cell and sodium out. That is called an electrogenic pump because it creates some electrical potential across the membrane. Calcium pump is also there, and that can also be part of the issue, but it's primarily the sodium-potassium ATPase. And what we have is minus 70. You also notice that I didn't talk about chloride. Chloride channels are also closed at this condition, so they are not part of the membrane potential, just like calcium and sodium.